the flat backside. Don't worry, I won't make you pull out your protractors in this class. Okay. All right. So moving along a bit, let's do a quick little example. Let's see what you need to know. You need to know, you need to remember that R for us is equal to M times N, or we can write it as R is equal to lambda over delta lambda, right? I threw out those equations on Friday, but it's good to know for this question. So I'm gonna put you in some breakout rooms and see how things go. How are we feeling?
Want to start?
The lines per millimeter.
Yeah.
Yeah, we're trying to turn that, use these two numbers as 600 lines per millimeter and the 25 millimeter long grating. Turn it
Do we
into
need the 25 millimeter part for now?
No.
No.
We need.
So on the previous one, it was 500, and what did we do with it?
We divided it.
Put 1 over 600.
Absolutely.
Is that the same as grooves?
Yeah, so lines and grooves are the same.
Oh.
Okay.
Okay. Okay.
Yeah, so these are lines that are etched in that diffraction grating.
Okay. Yeah.
So that's a good starting point. Lines and grooves are the same thing.
Yes, sir.
Yes.
Excellent, excellent. And so what's our groove distance?
I got like 0.0016.
There's a unit, no?
Oh, millimeter per groove.
Millimeters, yeah.
No.
So, yeah, so 0016 millimeters, yeah. They tend to shift that decimal 3 places and write as micrometers, right? Just so we don't have to deal with all those zeros.
Mm.
But yeah, absolutely. Did you get to
For-
B yet?
I got 15,000 grooves.
Same.
Excellent, excellent, absolutely. And if it's first order diffraction, what's that resolution?
15,000.
15,000. This is
So
not
it's the
hard.
same as the number of grooves.
As long as we're talking about first order diffraction, absolutely.
So that's the R equals MN
You bet.
equation.
You bet.
Okay.
Yeah, and so once you know R, you can use it to find the delta lambda in the next equation. That's part D.
Dr. Davis, and the R equals MN. What
Yeah.
is the M and what is the N?
M is the order, and N is the total number of lines, total number of grooves.
Oh.
So are there units for the resolution?
There's not, because it's order is unitless, and number is just a number of grooves.
Okay.
And so R is unitless. Yeah, good question. So how many grooves are on our grading?
15,000.
Excellent. So what do we get a resolution of?
We're thinking about 15,000.
I'm thinking that's about right.
Oh, okay.
Well, our N is supposed to be number of grooves illuminated. Do
Yeah.
we
and
just
so it is in instrument maker's best interest to illuminate the whole diffraction grading, right? So you get the best resolution. In reality, do all of them do that? No, but it's something that most instrument makers do, is to illuminate the whole width of the diffraction grading so that you get good resolution.
makes sense?
Okay.
And then once you know R, you can calculate the wavelength separation using the other equation.
Yep.
All right, just another minute. All right. So I think most of us got on the same page. Resolution was 15,000. Caroline brought up a good point that on Friday, when we talked about resolution being M times N, we said N was not just the total number of grooves, but the number of grooves illuminated. When we talk about the number of grooves illuminated, it is always in an instrument manufacturer's best interest to illuminate all the grooves so that you get the best resolution, right? While that's not done, 100%, right? Maybe they miss a few on either sort of extreme end of a grading. The assumption is often that the entire diffraction grading is illuminated. Right? And so with a resolution of 5,000, this is the first place where our textbook has, not the first place, but this is one place where our textbook has an error. It asks for first order diffraction, and then it uses 2 for M, right? So if you look in the textbook, C and D are going to be different than what we talk about because it used second order instead of first order. So we had a resolution of 15,000, right? And that is a unitless number. I don't remember who asked that, but it is a unitless number. And then part D, if we have a wavelength of 550 nanometers and a resolution of 15,000, what is the resolution we can get? What's that delta lambda?
3.6 times 10 to the negative 2
Unit?
nanometers.
Yeah. So, yeah. 0.037 nanometers or 37 picometers, if you want to think about it that way. Yeah. And so we can get pretty good resolution, right? In this particular instrument. Okay. Questions about that one?
How did it come out in nanometers? Is that just because it's a wavelength?
Yeah, so because our top unit was nanometers and R is unitless, the bottom unit
Okay,
nanometers, so that our units cancel.
gotcha.
Yeah, so if we were talking, so infrared doesn't use a grating. We'll talk about that when we get to IR. But if we were talking about infrared, those are micrometer kind of wavelengths rather than nanometer wavelengths. And so that wavelength would be in microns instead of nanometers. I hope you all cannot hear my cat's hairball at the moment. So one of the issues with a monochromator, a diffraction grating style monochromator, is that we do get these multiple order wavelength diffractions. And those diffractions can overlap, right? And so we have this issue of overlapping output. Right? So if you look here, you know, remember zero order is just a straight reflection. We do not get any wavelength separation in a zero order diffraction. I don't remember if I said that Friday, right? But since it's just a reflection, all the wavelengths that come in go out exactly the same angle because they're not separated at all. And so for a first order diffraction, you can see the first order and the second order overlap each other a bit here, and the second order and the third order overlap each other a bit here. Right? For a given wavelength, this is a good test question here. This end of our first order diffraction, is that going to be high wavelength or low wavelength? Long wavelength or short wavelength? Let me put it that way. It's
Short.
only, yeah, it's only shifted a tiny bit from the standard zero order reflection. And so this is our shortest wavelength, right? And here's our long wavelength. Right? So the longer the wavelength, the more it's shifted. The shorter the wavelength, the less it's shifted. Right? And so because of that, we have, if we sort of think just about this first and second order diffractions, here we have our short wavelength. And so if I'm interested in first order light and I'm interested in something, let me get a new color here. If I'm interested in something right here, well, I'm going to have that first order diffraction, but I'm also going to have some short wavelength second order diffraction that's coming through at exactly the same angle, right? And so almost all modern instrumentation has a series of filters that will change based on whatever wavelength you're analyzing, so that you block out certain wavelengths, right? And so these optical filters block out higher order diffraction. Right.
Can they detect that by just how does that work?
So it's not a detected thing, it's just an engineering thing. And so engineers say, okay, well, in this particular instrument setup, that overlap starts happening when our first order diffraction is at 535 nanometers. And so we're going to have a filter that pops in when somebody's measuring above 535 nanometers.
How do they distinguish the second order? Like, how does it filter if they come in through at the same wavelength?
Yeah, good question. So the types of filters, that's an excellent leading question here. The types of filters that we can have, right, there's three types. They're called high pass, low pass, and band gap. Right? And so if we have a high pass filter, anytime we talk about filters, we're always talking about frequency. So we kind of have to shift our mindset from wavelength to frequency, right? High frequency, low wavelength. And so if it's a high pass filter, right, this is going to allow high frequencies through, right? And high frequencies is low wavelength. Right? The low pass is exactly the opposite. It allows lower frequencies. That corresponds to higher wavelengths. And if we have a band gap, then, well, there's band gap and band pass, actually. A band gap is where a single frequency is blocked. Right? And so in this situation where we have that short wavelength from second order light, but a long wavelength from first order light, are we going to want a high pass, a low pass, or a band gap?
Are we trying to block out the second order?
Yeah, absolutely. Block out the second order.
So then a high pass?
So high pass is low wavelength, and we don't want these shorter wavelengths, right? We want to block those. So we actually want a low pass filter, so the longer wavelengths get through, but the shorter wavelengths get blocked.
When you say low wavelength and high wavelength, what is that? Does that correspond to like long or short?
Yeah, good. Good point. Yeah. Yeah, so a high pass allows short wavelengths through, a low pass allows long wavelengths through. Yeah. Okay. And so if we want to block out those shorter wavelengths from the second order reflection, diffraction, then we want to have a low pass filter that allows longer wavelengths to get through. And so almost all optical instrumentation has some kind of filter of this variety, as long as they use some kind of diffraction where you might have these second order interferences. Depending on the geometry of your instrument, so I mean, if we think about the way that this is arranged, this image is arranged, right? We're assuming that the light exits the instrument here, right? That's sort of what they're thinking. You can imagine that if the instrument were smaller and the light exited here, there'd be a whole lot more overlap, right? And so if we were to have an instrument that was much smaller, we'd have to have not only like a series of high and low pass filters together so that you can block the short wavelengths from second order to get out the longer wavelengths from the first order through, but then you also need to worry about the third order that's creeping in there, and so it can get a little complicated. But generally speaking, we want some low pass filters so we block out those higher order diffractions. All right. Okay. Linear dispersion. So this goes back kind of to what I was saying just now about sort of how far apart those different orders are spread. And so when we talk about linear dispersion, right, we have a single beam coming in, and when that beam exits the diffraction grating, it's going to be spread out, right? And so we have a way of calculating that dispersion. Let me go back just a minute here to this picture, right? This picture, our ray 1 and ray 2 are a single wavelength, right? And what it's showing is how a single wavelength bends on a diffraction grating. If our incident beam, however, is a whole bunch of wavelengths, then we're going to get those diffracted beams spreading across based on the differences in their wavelengths. So if the ones that are drawn are very short wavelengths, right, then we'll have longer wavelengths that go out kind of like this, and even longer wavelengths, I'll make it red because red is long wavelength, that go out, you know, even further, right? And so we get this spread of wavelengths, right? And when we talk about the linear dispersion of diffraction grating, we're talking about how much linear space, when it hits the wall of that monochromator, how much linear space are those wavelengths spread out across, right? And to get good resolution, do you think we want a lot of linear dispersion or not a lot of linear dispersion?
Not a lot. Right? So
So
you
if we're trying to separate our wavelengths,
so a
if
lot.
I can separate my wavelengths over 5 centimeters, then it's easier to pick out the one I want than if I can separate them only over 1 centimeter. Right? And so we actually want more linear dispersion because we want to be able to separate out those wavelengths. And so when we talk about linear dispersion, we're talking about the ability of a diffraction grating. Well, I won't say ability, I'll say the degree to which. The degree to which a diffraction grating disperses, I know it's not good to use the word in the definition, but there it is, lights slash wavelengths in space. And so forgive me for using just a single color here, right? But we're talking about, if that's my rainbow, right? This is, right? These are my options, right? I can have a low linear dispersion or a high linear dispersion. And if I'm trying to pick out a single wavelength out of a rainbow, the broader that rainbow is, the easier it is to pick out a single wavelength. And you know, this math is a little tricky because not all the rays, because they're, you know, sent out in a curve, there's not sent out. They're sent out sort of in this radial pattern, but they're all hitting a flat surface, and so some rays are traveling a bit farther than others. The math is a little in depth, but our book has an approximation that's pretty good. And so this linear dispersion D is about equal to the order M times F, where F is the focal length of that monochromator, divided by D, that spacing. And so again, M is the order, F is the focal length, and D is that groove spacing. Okay.
Dr. Davis.
Yes.
So you said that more linear dispersion gave a greater resolution, correct?
Yes. I want to be clear when we talk about resolution. Earlier in the last problem, we were talking about the resolution of a diffraction grating, right? And here we're sort of shifting to talking about the resolution of the instrument as a whole. Right?
Okay.
The resolution of the instrument as a whole depends upon the resolution of the grating, but it also takes into account a lot of other factors, including this linear dispersion. And what we'll wrap up today with talking about is the monochromator geometry, the exit slit width, especially.
Okay. But then with the low versus high
Yes.
dispersion, you said it'd be easier to pick out a wavelength from the high.
Absolutely. So getting a little bit ahead of ourselves, but maybe it's a good time to talk about it, right? In order for us to use, I mean, think about a UV vis, right? You have a light source and you want a single wavelength out, right? You set your UV vis to look at 505 nanometers or something, right? What the instrument is doing is it takes that white light source, shines it on a diffraction grating, splits it up, and then selects 505 nanometers. If I have a low dispersion instrument and it's like, that's my slit width, well, there's a whole lot of wavelengths that are getting through there, more than just 505, right? If I have a high linear dispersion instrument and the same slit width, I have a much lower number of wavelengths, a much smaller range of wavelengths that are actually getting through to go to the sample. All right, a real quick problem on linear dispersion. Since you're already working hard, I'll let you stay here, I suppose. Feel free to chit chat amongst yourselves.
Dr. Davis, do we need to know if this is first order or second order?
So we almost always use first order diffraction, only because it's the one where most of the power is. And
Okay.
we're almost always looking for the most power.
Okay.
I just forgot I was sharing my screen. So, hopefully you're following along at home. Did you get the same resolution for both diffraction gratings? Yeah, excellent.
Yep.
And so, perhaps I should have mentioned this before I let you loose on a problem. When we talk about the linear dispersion, we sort of want to know how wide a wavelength might be spread, right? And so we measure wavelength for UV vis, at least in nanometers. And our slit widths, the exit on our monochrometer is often in millimeters. And so we want to know how many millimeters of linear distance is each nanometer of light spread across. And so I converted meters to millimeters, right? That focal length of 0.3 meters, I converted it to millimeters. And then I converted the D, that groove spacing, into nanometers. Right? And so for the 600 lines per millimeter diffraction grating, we got a dispersion of 0.18 millimeters per nanometer. To put that in some context, if we had a 1 millimeter slit width, right? If we had a 1 millimeter slit width, then we'd have about 5 nanometers worth of light get through. Does that make sense when I say it that way? So this linear dispersion is saying that every nanometer of light, when it's spread out, every nanometer of light takes up 0.18 millimeters, right? And so when my light is spread out and it passes through a 1 millimeter opening, about 5 nanometers worth of light come through, right? So again, if I was talking about by 505 nanometers, maybe it's 505 to 510. All of those wavelengths are getting through that slit, right? Whereas if I go over here, right, this is about a third, right? I'm just estimating, but this is about 3 nanometers of light, and so that's only 505 to 508, right? I have a much less light that I don't care about getting through. Are you following? Does that make sense? Yes, no, maybe?
So, are you saying that you want less to get? You want less anyway?
So if I'm only interested in seeing how much my molecule absorbs 505 nanometers, then I really only want to look at 505 nanometers, not 506 and 507 and 508 and 509 and 510. Right? I only want 505. And so it is a good thing to have less light coming out of the instrument, a narrower range of light coming out of the instrument.
So that means that the 1200 grooves per millimeter would be better to use because it's got like the lines are more spread out.
Absolutely, absolutely, yeah. So if I were to draw a similar image here, right, it would be the same range of wavelengths would be much more spread out, and so I'm getting fewer extraneous wavelengths that come through the monochromatic. This introduces a concept called bandwidth, which we'll talk more about in chapter 5. Right? And when we talk about bandwidth, right, this is sort of the range of frequencies in a particular experiment. And depending on your experiment, you might want a high bandwidth, you might want a low bandwidth. But for spectroscopy in particular, we generally want a lower bandwidth so that we're looking at just the wavelength we want to be looking at. Yeah, and so this is the better choice.
Dr. Davis, what are the units for the groove spacing when we do like for the 1200 when we do 1 over 1200? Is that just
Yeah, so
millimeters?
so you can leave it in millimeters is fine. Again, because it's often, you know, a small fraction of a millimeter, we usually convert it to microns. I think in the previous problem it was 0.17 microns or something, and so
Okay.
instead of writing it as 0.0017 millimeters, we just switch the unit.
Okay.
Here it's in nanometers only because we're going to equate it to the wavelengths of light that we're using, and in UV-Vis we use nanometers. Could you have left it as millimeters? Sure, absolutely. But talking about how many millimeters of the millimeter range of light getting through is kind of useless when we're talking about nanometers. You know, 505 nanometers, I don't want to convert that to millimeters just to talk about it. Okay. All right, so then this last bit, by talking about monochrometers, coming back to this image that we saw Friday, we have this entrance slit, and really we want this to be as large as possible so that we get the most power from our light source, right? So the balance for our entrance slit, we want it to be large for power. Right? But we have to temper that. We don't want to let in all kinds of stray light, right? We want to make sure that it's only the light we're interested in. It's only the light from our light source. We don't want room light. We don't want light from a cell phone. You know, we don't want any kind of other crazy light. And so it's going to be relatively small so we don't let in stray light. Right? And the entrance slit is almost always bigger than the exit slit, even though that's not shown in this particular image. Right, so we go to this first mirror. I think I said it on Friday, but this is a collimating mirror. Remember, collimating is where we get all of our waves going in the same direction. Right? Dispersed is what's happening here, right? Where they're, as we go away from that entrance slit, they spread out. The collimating mirror means that they travel in a straight line. They don't diverge. And so we have that collimating mirror to our diffraction grating. You can see here that, of course, the goal is to illuminate as much of that diffraction grating as possible, right? We talked about that earlier. If you have all those grooves, you might as well illuminate them all, right? And then you get your diffraction. This is not really an anti-collimating mirror, but it's more, we call it a focusing mirror, right? We take that collimated beam and we focus it back down to our exit slit. Right? And that exit slit, I know it's 920. I know it's 920. That exit slit, I'm just going to give you this equation. The bandwidth, that range of wavelengths we get out is equal to the size of the slit divided by that linear dispersion. Right? And so just real quick, if we had 1 millimeter divided by 0.36 millimeters per nanometer, right? That's where we get our about 3 nanometers coming from as our bandwidth. Okay. There's another practice problem there, and then that last slide has the homework for chapter 3, right? If you want, we can talk about this practice problem on Wednesday. Okay. And then those are the homework. For question 4, you do not have to plot it in Excel. Just calculate what the correct radius should be. Right? If you were a real engineer, you wouldn't plot it and you then go, oh, it should be right here. You'd plug it into an equation and figure out what it should be. Okie doke. Sorry I went over. Hope you're not late to your next class.
Hey, Dr.
Hi.
Davis, what did
Yeah.
you say about bandwidth again?
So bandwidth, this is the range of frequencies is usually how we talk about it, but it can also be the range of wavelengths.
Okay.
That are actually used in the experiment, right? And so for some
And
experiments,
that's just called the bandwidth.
yeah, and we'll talk about that more in chapter 5 next time. Well, I don't know if we'll get to next time, but chapter 5 is up next, and we'll talk more about bandwidth there.
Okay. All right. That sounds good. Thank you, Dr. Davis.
Sure, absolutely.
I'll see you later.
Take care.